In this section, we consider how to use numerical methods, in this case, what's called Euler's method, to approximate a solution to a differential equation. Mathematicians often care about the general solution to a problem. However, in application, that is not always desirable or even possible to find. However, there are methods which are often called numerical methods that allow you to approximate solutions even if an exact solution is not possible or at least not feasible to find. To approximate values of the solution near a particular point, we can use linearization. We can use basically the tangent line that we learn about in Cal 1 to approximate a solution curve using those tangent lines. So what we want to do here is consider an initial value problem. Nothing in particular right now, just the initial value problem in the generic form, y prime equals f of xy, and an initial condition, f at x naught is equal to y naught. Okay, now let's assume this equation has a solution curve, which may or may not be true, right? After all, solutions, some equations just won't have solutions. But let's assume that it does exist. Even you say, okay, well, what is it? Well, we don't know. If we knew that, then this wouldn't be a problem worth considering. Okay, so you have some unknown solution curve. Okay, so here we have a solution curve, which is unknown. You say, well, that's going to be pretty hard to draw if you don't know anything. You're just going to draw a blank grid. Well, we know something, just a little bit though. We know the initial conditions. We know that at some value, which we'll call x naught, here's our x naught, that you will have the value y naught on your graph. So here's your y naught. Okay, great. So you know one point out of an infinite number of points on a curve. Well, okay, that's not great. Well, it's not bad though. Well, what do you mean? 1 point out of an infinite number? That's terrible. You know basically nothing. Okay, but well, what is it that we're trying to find? Well, let's say that I'm the omniscient creator of heaven, earth, and mathematics. Let's say I know what the solution curve looks like, even if no one else on earth does. Let's say that's my solution curve there. Okay, and as a mathematician, as an engineer, as a physicist, your goal is to figure out what I know, to figure out what this curve is. Okay, but I don't know. All I know is this one point. Well, you know one other thing about it. You know the derivative. Because yes, this is a differential equation. But if you think about it from a Cal 1 point of view, this is the slope of your tangent line. This is y prime. So if I know this equation, which of course I know it, it's something I'm trying to solve, I can then use it to find a tangent line. Okay, so my tangent line here would look something like this. Okay. Well, we know the tangent line is a terrible approximation, right? We've known that since Cal 1. Tangent lines are really, really not good approximations. That's the whole point of a Taylor series. In Cal 2, we learned to make better approximations. Oh, well, you know, a linear approximation isn't terrible as long as you don't go too far away from your initial point. So let me go just a tiny, tiny distance away. I'll use the same notation that I use in Cal 1. I'll say h is my little distance. So as long as I don't go too far away, this is x naught plus h. And then this is a point that I'm saying, oh, I believe this is the next point on my curve. Now, of course, as an engineer or a mathematician, or a physicist, or you're trying to figure out this curve. And clearly, as the one being who knows the actual curve, I'm looking at you and going, yeah, that's really not that close. But you're not done. Because now you can say, well, from this point, what's the tangent line? After all, I know the tangent line for any point in space here. Any point x comma y. Notice that x comma y ideally is on my curve. That's the solution I want. But really, this is for any x and y. And that includes this point here. So now I can find the tangent line at this point. Oh, well, it'll look like this. And if I go a little further out from there, if I go another h this way, this would be x naught plus 2h. Notice that point is still not great, but not bad. If I then find the tangent line at that point, notice it is following the curve, because the curve is giving me the slope. Mind you, I'm not actually on the curve, but I'm following the curve at a rate that's in a direction that's not too bad, at a distance that's not too bad. If I then take another small step, which I'll call it again h, so this would be x naught plus 3h. Notice that point is actually on the curve, just kind of accidentally. And if I keep going, I'm going to create my own curve, which may not be the correct curve. In fact, it's almost impossible for it to be the correct curve. But the curve that I'll create will be one that is exceedingly close to the actual one, even though I never actually found the actual one, even though it was impossible for me to ever find the actual one. This is what's called a numerical method, and it uses an initial condition along with some given information, in this case the slope of a tangent line, to approximate the path of my solution curve, even if and when I cannot actually find it. So let's see how we develop that computationally. Because one thing is, drawing a picture, but another thing is actually being able to complete the computation. All right, so I have a point slope form of a line. Right? Here, I happen to know a single point that is perfect. That one I know is on the line. The other ones may or may not be, probably not, maybe accidentally, but the first one is definitely on my curve because it's an initial condition. So let me go ahead and plug in my x naught and my y naught into a linear equation. So I get y minus y naught equals m times x minus x naught. This is what's called the point slope form of a line. If you think really hard back to your high school algebra, you will almost certainly remember this form. Here, y naught is the y value of the point that's known to us. Well, we were calling it y naught anyways, so I think I'll continue calling it y naught. X naught is the x value of the point that's known to us, which again, it was already called x naught, so nothing changes there. But then our slope, well, the slope is the derivative of our curve. That's our function, that's our f of xy. So this will be f of xy, because that slope is found by taking the derivative of our curve. That derivative is f, which means our slope is f. Now, of course, here I can go ahead and just bring this to the other side to isolate my y, and I get y equals y naught plus f of x comma y, and actually it's not f of x comma y, it's f of x comma y specifically at that point. So it should be x naught comma y naught, because there's going to be different slopes. I want the slope specifically at the starting point. Like this, so f of x naught y naught times x minus x naught. So let's say I wanted to use this to find my next point. Okay, well, the next point that I want is going to be, I'm looking for my next y value. I know my next x value. My next x value is just going to be the original x value plus a little h. Okay, so my next y value, I'll call it y1, because I started at y0, so I'll call the next one y1, is equal to y0 plus f of x0 comma y0, times, now my new x is not a mystery to me. It's my original x plus that little h that I've decided to add, and then minus x naught. Notice that these two just cancel out, here and here, and we're left with y1 is equal to y0 plus f of x0 comma y0 times h. And I think I'll put the h in the front right here, this h right there. But now that you've moved on to this next one, you can repeat the process to find the next one. And then repeating that process, we'll move on to the next one. And as long as your h, as long as your step size is sufficiently small, as long as it's something like, 0.1, 0.01, something very small, your curve that you create will follow along, will be an approximate curve to the actual solution. All right. So the way this works is called Euler's method. So here the general form is, if you want to find the next y value, you start off by taking the previous y value, the one you were just at, plus h, your step size, times f at your previous y values. sorry, your previous x and y values. So xn, comma yn. And it's just this, but just repeating the process for the next one, for the next one, for the next one, and so forth and so on. This gives a recursive algorithm. It tells you if you have x naught, y naught, you can find y1. If you have then x1, y1, you can find y2. If you have x2, y2, you can find y3, and so forth and so on, until you have as many points as you need along your curve. Here, which gives a recursive algorithm to find an approximation to the solution curve. N plus 1 steps of length h from our initial x value, from x naught. This thing right here, this process is called Euler's method. So let's consider an example where we go ahead and do this. One of the nice things about Euler's method is that although there is an error between your curve and the actual solution curve, the unknown solution curve, that error doesn't seem to build. In other words, the error that you get from the first step is not necessarily going to get bigger for the next one. In fact, in some cases, it gets smaller from one iteration to the next. So it continuously follows your curve, and the error, although there will always be some error, does not accumulate. So it doesn't get worse as you move further along. So here, let's consider an example. Let's approximate a point on the solution curve of the initial value problem y prime equals x plus y, where y at 0 is known to be 1, that has a step size h equal to 0.1. I'm not sure why I put parentheses there. That has h equal to 0.1. So that'll be our step size each time. All right. Okay, so that will be, well, let's choose n to be 0 because we're starting at x0, y0. So that's going to be, where n is equal to 0, we'll have y1 equals y0 plus h f at x0, y0. That is to say, well, let's see, our initial x naught, that's going to be 0, and our y naught will be 1. So that'll be 1 plus 0.1 times f of 0, comma 1. Okay? But this is our f. Our f being x plus y right here. This right here is f of xy. So right here, this is going to be 1 plus 0.1 times, and your function just tells you to add the x and the y together. So this would be 0 plus 1. So that's 1 times 0.1 is 0.1 plus 1 is 1.1. Okay? So what this tells us is that, yes, we started off with the point, what is that? X is equal to 0, y is equal to 1. But now we have the point, all right, our x value has increased by 0.1. So from 0, we now have 0.1. Our y value is now 1.1. And that would be another point on my solution curve. We can proceed. We can continue with this. We can do as many of these as we like. So now, if we say n is equal to 1, well, then that's going to be 1 plus 1, that would be y2, is equal to y1 plus h times f of x1, y1, like that, which our y1, well, that's our new y value, that's our 1.1, plus our h is still 0.1, that's our step size every time, and then we want f of the x1, y1 that we had before, so 1.1 and 0.1. 0.1 and 1.1. So that's going to be 1.1 plus 0.1 times the sum, 0.1 plus 1.1. So that'll be what? 1.2 times 0.1 is 0.12, and 0.12 times 1.1, that's going to be 1.22. Like that. So that gives us another point. That would be, so every time we take a step, our x value increases by 0.1. We were already at 0.1, so our next one would be 0.2, and our new y value is going to be 1.22. And if you proceed, you can find 0.3 comma something, 0.4 comma something, 0.5 comma something, and if you have enough of those, you can connect those as far out as you need to. And if you need to go from 0 to 10, well, then keep going until you reach 10. It might take you a while. Of course, this is the kind of thing you usually do with a computer, not manually, but you go out as far as you need to, connect those dots, and that curve will be an approximate solution. It will not be exactly correct, but it will be fairly close. Incidentally, just to compare how close it is, this equation right here is solvable, by the way. This isn't something that we would need to use Newton's method for, sorry, not Newton's method, Euler's method for. It's just I use this as an example. But, so here, note, we actually can find the solution to a problem like this, and in fact we will in chapter 4. So here, note, the solution to this IVP is given by y equals 2e to the power x minus x minus 1. We'll learn how to solve things like this in a later chapter. When you have this solution, note that we can actually plug in, now obviously if you plug in 0, you're going to get 1, right? That's, if this is the solution to this initial value problem, then 0, 1 must be on this curve. But let's see what happens when we plug in these other two numbers. So here, if I take y at 0, I'm definitely going to get 1. And in fact, you don't even have to take my word for that. You can check. E to the 0 is 1. 2 times 1 is 2. 2 minus 1 is 1. Minus another 1 is 0. Oh, sorry, I'm plugging in 0, aren't I? That's going to be 2 minus 0 is 2. Minus 1 is 1. So 2 minus 1 is 1. So if I plug in zeros, I get 1. If I plug in 0, I get 1. But if I plug in, let's see, 0.1, it probably won't be 1.1, but let's see what it actually is. It's going to be 2e to the 0.1 minus 0.1 minus 1. And that is not something I'm about to do off the top of my head. Let's grab a calculator here. 0.1 times 2 minus 0.1 minus 1. And it's actually 1.1103. 1.1103, which I got 1.1. That's not bad. Let's see what our next one is. If I plug in 0.2, it's going to be 2e to the 0.2 minus 0.2 minus 1. And that will be 0.2. Exponentiate that times 2 minus 0.2 minus 1. From my approximation, I got 1.22. The actual answer is 1.2428. Which again, not great, but not bad at all. These errors are not necessarily going to accumulate, which means if I keep going here, the next one, 0.3, 0.4, 0.5, some of them may move slightly further away from the actual curve, and some of them might actually move closer. Occasionally, you might even accidentally get one that's exactly this value. But in any event, it is never meant to be perfect, even if it is accidentally so once in a while. It is an approximation, and frankly, it's not a bad approximation there at all. So that is it for this section, and that's it for this topic. If anybody has any questions, comments, or problems, please reach out. Hope you all have a nice day.